So I'm going to go into this fault trace mapping application. So this is a movie just showing a little bit of the San Andreas with a couple of hill shades. It's going in a second, but it's kind of a quick tour and emphasizes the strike slip geomorphology. So, this is the Google Earth view with these traces. So here's a piece of the, this would be, I think this is, these are all B4 LiDAR data, so sort of 1 meter per pixel strip along the fault zone. You see really spectacular sort of tectonic landforms at Park Field. This is Card Hill right here. And, you can see that then if we go fly down to part of the Carrizo Plain, you can see additional landforms. So we see kind of this sort of discontinuous structural geology that defines the fault zone, and then interesting tectonic features, landforms that sort of cross the fault. So we'll see some of these kind of weird channels. And this is not so weird. This is the famous Wallace Creek offset, looking kind of along the fault zone. And so sometimes I just love the kind of touring through the data. So here, as I showed already, this is Feeling Creek offsets. This beautiful kind of tectonic sag there. Keep flying along. It's just kind of like a dark seismic site. This is an area where there's 2 strands of the San Andreas that are probably active at the same time with these blocks moving up and down between them. And then we'll go down. This is like where I did my PhD work. This is called the Dragon's Back right here. And some secondary structures, some normal faults, and maybe a little fold out there along the San Andreas. So main San Andreas traces through there. I will fly down. I think we're just going to go to El Mayor Cucupa. So that was a place where there hadn't been an earthquake for 150 years now. We can zoom into this data set that was gathered right after the 2010 earthquake and zoom right down to the fine-scale representation of the rupture at the El Mayor. So one of the things about mapping the fault traces is, this is a long-standing challenge, and people have identified a lot of interesting features in this landscape. So USGS mapped all the main active faults, sort of 1970s, mostly with aerial photography and field mapping. And so one of the things we did early published in 2009 was kind of comparing some field work that we had done with kind of just office-based mapping on the hillshades.
I have a quick question.
Yeah.
On the last one you showed, the El Mayor rupture, is that because they're vertical offsets? I mean, it was a strike slip fault, but you're seeing it because there's vertical?
Yeah. So, and I dove in that area there where there's more of the extensional signal, just to make it easier to see. So here's the same data. So the same hillshade of this piece of this south central San Andreas fault. So kind of in that Carrizo Plain area, just to the northwest. And so it's the same hillshade in all 3 cases, but then showing different mapping that came from different sources. So here's the digitized version of USGS mapping. Here's the field mapping that I did with one of my students, and then here's mapping that was done in the office. And so you can see that, the USGS scientists sort of gave a very discontinuous representation of the fault zone with some of these kind of features. They identified swales, scarplets, and then when we were in the field, we were really strictly mapping, and this was without any LiDAR topography. So this was just with aerial photos, but walking around. So we could really represent the main active traces and some of the landslides, whereas when Olaf was working in the office, so like Dilke was a student who worked with me several years ago, he also could pick off the main active traces. He would have a harder time in this complex zone, but then he identified some secondary features as well. So I think one lesson that we have learned over the years is that purely virtual work isn't enough. You've got to go in the field. But it is very efficient to get some data right away. And so some kind of combination of these two may be quite good. This also will be the case for the offset studies, is that it's easy to map from the office. It's hard to map in the field, so there's a constant tension between the two, and we'll never stop just mapping from the office, and it can be quite efficient, but there's always a need to kind of do some field checking.
How often does LiDAR maybe give you the opportunity to disprove what you saw in the field? Does that occur where you see something in the LiDAR and you're like, okay, my interpretation of the field is bogus?
That's a really great question, because different people have different attitudes, right? Like many people would say, well, if you saw it in the field, it's the better observation. Versus, the thing is, there are some words, a paper written by Leenkamper et al. About offsets on the north, in Chelan. He argued that sometimes when you're in the field, especially when you're working on offset landforms, you have a lot of foreshortening and other experiences in the field which limit your objectivity. Whereas when you're looking down from in the office at the landforms, you might you have a more objective perspective, and you can look at it from multiple views. It's also easy to share the observations. See, I saw this, whereas you can't take people in the field. So it's kind of an interesting philosophical point of sort of where you stand and then how often one sort of trumps the other. I don't think there's anything really systematic.
Another question. So if you extend the upper blue line to the top of the red blob in the middle above, there's a whole bunch of linear offset stream. How come that nobody mapped that?
It's right in here.
Yeah.
Well, because we were really emphasizing what we thought were the youngest landforms, youngest active faults. And so these were features we thought, they were probably following some structure, but they're not showing evidently sharp disruptions. And so we didn't map them, but it is a good point. Like if we put another layer on of kind of every suspicious lineament, there would be even many, many more.
So why did he pick that blue one that extends into it as a secondary trace, but not?
I think, actually, it's a good question. I think he was also, if you look sometimes in 3D estimates, there's kind of a little bit of a domal feature here. So I think he was trying to pick off that maybe there was a kind of a little bit of a blind structure there. He's trying to emphasize, but good question. I wonder sometimes why more of these weren't done, but as I said, we were really sort of emphasizing that narrow swath of most active features. Okay, so keep going on this topic for a little bit. So that last example was just looking at the pretty pictures, drawing the lines, basically. But another thing you can do is to look at more quantitative use of the data. So this would be basically computing topographic roughness from the digital elevation models of these alluvial fans in Death Valley. So this work was done by Kurt Frankel and James Dolan. And what they did is if you have a pixel like here at IJ, you kind of take the neighboring pixels and you can basically compute some kind of sum of squared differences of elevation. So if this number is small, it means it's a pretty smooth zone. And if it's a high number, it means it's pretty rough at this short length scale. And so you move this little computational kernel over the landscape, and you can find, then you can represent this as an angle, but it's also really a length. And so you can find that parts of these alluvial fans are quite smooth, and other alluvial fan surfaces are quite rough. And so what he can show is that if you take the mapping, which was done, refined by the high-resolution topography as well, that the surface roughness is kind of changing with age. And so there's kind of an optimal 70,000-year-old alluvial fan surface that's the smoothest. And so we could kind of take individual dates and then sort of correlate them across the mapping area using a topographic metric like roughness. So this is a really valuable approach that I think we're going to start seeing used more and more. So and then I've been talking about some of these metrics lately, especially with Andrew, because what we realize is there's so much data out there, and you can't really just always maybe map just on hill shapes. You want to compute topographic metrics. So you can do simple ones like these, where you're doing local calculations on the DEM, but you can also do more complex calculations. So this is a wavelet-based approach where in this paper by Hilly et al., where basically you could take, like, this would be the topographic profile, so sort of distance versus height. That's the scarp. And this would be the first derivative, so that's the slope, so it's steepest in the middle of the scarp. And then this is the second derivative, so that's the curvature, so it's highest curvature at the top and the bottom of the scarp. So basically what George did was to take this sort of form, call it a wavelet, and kind of move it around in a 250 meter long section, just kind of move it through the topography and try to find where it might fit some of the points. So this is kind of a sort of a, not that pretty view, but you can see as he moved around, he could kind of fit some of these points and show that in cases it was very high curvature, which would mean a young, sharp fault scarp. In other places, it was more subdued, low curvature. And so that's what the color is showing, is basically the curvature of the age, the inferred age of the fault scarp. And so what you can see is here in the Carrizo Plain on this 1 meter data set, he found the fault automatically. We also found a lot of the fluvial scarps, which is a very interesting for study faulting. So then here he could sort of filter it by orientation. So just pick off the northwest trending fault scarps and not worry about maybe these more northeast trending fluvial scarps, and then identify pretty well the main fault traces, kind of semi-automatically. And also sort of talk about relative age or relative sharpness. So this is I think, going forward, a big area for us is to start to build these tools up so that we can hunt around more semi-automatically through these billions of points. Here, we showed a lot of strike slip examples. Here's a Teton fault zone. So you can see the 10 meter per pixel US GS data with the main fault traces as part of the Teton fault. And here it is. Here's the digital terrain model digital surface model, so with the vegetation. And you can see some things along here, but when we pull the trees out, filter it, you can really see the quite spectacular tectonic landforms of this big normal fault. But you also see really nice moraines of where the glaciers were around there. So good applications and beyond just strike slip.